In number 28, we want to use the alternate form of the definition of the derivative to show that f prime of 2, we want to show that f prime of 2 does not exist for f of x is equal to x minus 2 to the 2/3. All right, alternate definition, f prime of 2, that's the limit as x goes to 2, f of x minus f of 2 over x minus 2. All right, substituting in what we have limit x goes to 2. We'll substitute in for f of x minus 2 to the 2/3. F of 2 is 0. Okay, so that's the limit as x goes to 2. X minus 2 to the 2/3 over x minus 2. Again, 0 over 0 limit, but we can just simplify this by subtracting exponents. This is x minus 2 to the 2/3, x minus 2 to the 1. 2/3 minus 1 is minus 1/3. All right, so this is the limit as x goes to 2 of 1 over x minus 2 to the 1/3. So here we have what I call a 1 over 0 limit. In other words, this is going to 0. This goes to 0. And the numerator stays at 1. It's a 1 over 0 limit. So this is either infinity or minus infinity, but in any case, this limit does not exist. So it's a 1 over 0 limit. Okay, it's what we called an infinite limit. It doesn't exist. So that shows that f prime of 2 does not exist. Okay. In number 29, we want an example of a function f of x which is continuous at x equals 0, but f prime of 0, the derivative, does not exist. So a typical example would be the absolute value function. Is 0, f of x is equal to the absolute value of x. This is continuous at x equals 0. Let's just talk about the picture itself. It is continuous at x equals 0, no breaks, no points removed. So it does appear to be continuous. And it does also appear to have a derivative that doesn't exist because of this point here. In general, when a function comes to a sharp point, the derivative doesn't exist at that point. Okay, so that's just how it appears, but now we have to show actually that the derivative does not exist. So what is this function equal to? Well, if we open up the absolute value of x, this is equal to minus x when x is less than or equal to 0, and x when x is greater than 0. We could have put this less than or the equal to here or here, either one. Any case, we opened up the absolute value. In fact, I'd rather put it in the denominator, on the bottom line, because that's more standard. Okay, there I switched the greater than or equal to the second line. Okay, so here's our function f of x. Let's show that we want to show that that f prime of 0 does not exist. Let's use the alternate form of the derivative. So we want to show that the limit as x goes to 0 of f of x minus f of 0, which is 0, over x minus 0 does not exist. Okay, that's what we want to show. So we want to show that, well, first of all, what is f of x? Well, f of x is equal to minus x when x is less than 0, and it's equal to x when x is greater than or equal to 0. So we have to break up this limit into a left-hand limit and a right-hand limit. To the left of 0, we're going to use this expression for f of x, and to the right of 0, we're using this expression to f of x. So this has to be broken up into two limits, a left and a right. Okay, so first we look at the limit as x goes to 0 from the left of minus x minus 0 over x. From the left, the limit is minus 1. And the limit as x goes to 0 from the right, we have x minus 0 over x. So from the right, it's equal to 1. So we see the left-hand limit is not equal to the right-hand limit. So that implies that the limit as x goes to 0 of f of x, let's just write, now we'll go back to the absolute value of x, does not exist. Okay, so f of x equal to the absolute value of x is an example of a function that's continuous at x equals 0, but the derivative does not exist. In number 30, we're just looking at some pictures, and just from the picture, we're going to see different cases where a derivative doesn't exist at x equal 2, different things that can go on. Okay, here's one picture, and this is what we looked at in the previous example. If you have a function that basically comes to a point, or a function that's made up of two lines that meet, these two lines meet at x equal 2, the derivative will not exist here. All right, this is one type of place where the derivative doesn't exist. Okay, here's another point where the derivative may not exist. In this case, we have a infinite tangent line here. All right, now, so here the derivative is infinite, so in that case the derivative doesn't exist. Let me give you an example of a function. Well, we saw this also, we saw something like this in the previous example. The function would be y equal x to the 1/3. That function is similar to this one. Y equal x to the 1/3 looks something like this. Just sort of flipped around. Here we have a vertical tangent line. So this is y equal x to the 1/3, something like this. And we have a vertical tangent line at x equals 0. So we could say that y prime does not exist at x equals 0. So that's another typical function where a derivative doesn't exist, and this one actually is continuous. Now here, if a function is discontinuous, all right, the derivative does not exist. In general, a function must be continuous for the derivative to exist. All right, so here the derivative doesn't exist because it's discontinuous. We will show that f prime of x exists if f prime of x exists. that implies that f of x is continuous.